session. So, Petr, are you online?
Joe, I'm not sure if you can hear me, but I'm here.
Yes. Okay. So it's my pleasure to introduce the first speaker, Petr Kravchuk from the Institute of Advanced Study, and he will tell us about Lorentzian conformal field theory and uses of Lightray operators. Go ahead.
Yeah. So let me share my screen first. All right, can you see the screen? Hopefully, yes.
Yes.
Thank you very much for the introduction and for the invitation to give a talk. So today I'll be discussing the work I've been doing with this set of collaborators, Han Chan, Murat Kaloglu, David Simonsdef, and Sasha Zabayedov. And it's described mostly in this works, and it's related to Lightray Creators and Lorentzian properties of conformal theories. So the outline for the talk is going to be roughly as follows. I will start with some motivation from the point of view of describing various Euclidean Lorentzian singularities of correlation functions and CFTs. And this will lead us to introduce the Lightray operators and their radio trajectories. And after discussing this technology for a little bit, I'll give one nice application to energy-energy correlation functions and a nice connection to conformal representation theory. So in this talk, I'm going to be discussing conformal field theories in space-time dimensions at least 3. And we, of course, like to discuss conformal field theories because they're so useful in many contexts. Just to name a few, they describe fixed points of RG flows. So they're relevant for scale limits of critical points, long distance physics of gaseous quantum field theories, etc. They're also related to quantum gravity by the CFT correspondence, and everybody loves quantum gravity, so it's also a great reason to study them. And more generally, you can just approach the study of CFTs as a way, as a starting point for studying more general quantum field theories, either just as a more simple class of examples, or you can also imagine deforming conformal field theories by relevant deformations and getting more general PFTs out of that. So hopefully studying conformal field theories will teach us more general lessons about general PFTs. And when we discuss conformal field theories as a class, we like to think about them in terms of, we often think about them as a set of local operators and as their correlation functions. So that we can have some operators, so 1 through ON, and we can have their various endpoint functions. And in this talk, I'll just focus on correlation functions in flat space. Of course, these correlation functions are subject to some conditions such as conformal symmetry, unitarity, crossing symmetry, etc. And we like to use these conditions to learn new things about our theories. But we can do this in 2 different ways, which are related but not exactly the same. So we can study our correlation functions in Euclidean signature or in Lorentzian signature. And usually we don't distinguish this very much, and rightly so, because Asrad and Schrader a long time ago have proved equivalence theorems, which say that these 2 descriptions are mostly equivalent. And if you have Euclidean correlators, you can analytically continue them and obtain Lorentzian correlators and vice versa. I say almost because there are actually some open technical questions to this day in this story, which we reviewed recently in a paper with Slava Rychkov and Justin Chow, but it's not going to be particularly important for this talk. So even though the Euclidean Lorentzian correlation functions encode the same information, they kind of make different aspects more easily accessible. So let's say if you focus on Euclidean correlators, then away from coincident points, there are just some smooth functions which can be computed by the usual operator product expansion. And since they're smooth away from coincident points, the only interesting thing that can happen is that as we move the points around, some of them might collide. And the LPE provides a perfect tool for studying these coincident point singularities, because if you compute these coefficient functions that appear, they're proportional to the powers of the distances. And so the LPE expansion just becomes an expansion in powers of the small parameter near our singularities. And so it gives us a complete description. If we go to Lorentzian signature, on the other hand, it's still true that we can compute all our correlation functions by some convergent P's, but now we have many more interesting limits to consider. So in addition to the kind of coincident point singularities, we can also consider more general situations when we have some local operator approaching the light cone of another operator. And what's even more interesting is that not only this can happen, but also we can have, say, O1 approaching the light cone of O2, and there can be some third operator far away, which can have a null cone which separates these two operators from each other all the way along this limit. And this can really mess with the LP, and in particular, it turns out that there are many interesting singularities of Lorentzian and correlation functions which cannot be easily controlled by the local LP, in the sense that if you take a situation like here, for example, it might turn out that it seems like we want to use the OP between O1 and O2 to understand what's happening, but this OP might turn out to be divergent. And there are many such examples, but today I want to focus on one particular simple case, just for the sake of time, and it is the energy-energy correlators studied by Hoffman-Molesena, and I will describe them in more detail in a couple of minutes, but just generally speaking, the way you can think about them is that we select some null plane, for example, given by x plus equals 0, insert some sort of spectator operators below and above this null plane in our correlation function, and most importantly, we insert two null integrals of stress tensors on this null plane separated by some transverse distance. And we ask what happens when these two null integrals come close to each other. So naively, it might seem like a good idea to take the LP between the two stress tensors, because in the limit when this null lines approach each other, all the points in the integration contours become null separated, and the P seems to give some interesting information about that. But if you start analyzing this more closely, you find that in the integration region, in the integration domain, there are regions where the subleads divergence. In particular, if one of the operators moves to kind of past null infinity and the other moves to the future null infinity, this corresponds to something that's known as a radial limit, and it's known that the LP between two stress tensors will diverge. So we cannot use it to understand this behavior, and this makes it a complicated problem, even though, as I'll explain, it's physically interesting. And this particular problem was studied by Hoffman and Molesena, as I said, and as other people in other circumstances, they have found that the useful thing to do, or at least the thing that seems to be needed for describing such singularities, is being able to analytically continue various data of local operators, such as scaling dimensions and Lorentz spins, to scaling dimensions and OP coefficients to non-integer values of Lorentz spin. While this has been appreciated for a while, the existence of such analytic continuation was only shown relatively recently by Kravchuk in 2017, and where he derived Lorentzian inversion formula, which is a CFT analog of Forsyth-Grieber formula, and it basically proves that some conformal partial waves are analytic functions of spin. In some follow-up work with Davidson and Steffen, we have shown that one can interpret this Lorentzian inversion formula, or since lift it to some operator language in terms of non-local Lightray operators. And in this language, some already known formulas, for example, those appearing from already theory, take a simpler and natural form in some appropriate sense. So the goal for the rest of the talk will be to describe these Lightray operators and explain how they are useful for studying this particular problem for the energy-energy correlators. Now, in order to introduce the Lightray operators, I first need to introduce something which we call the light transform. For that, we first need a bit of notation for the local operators. So in this talk, I'll only focus on local operators which are traceless symmetric tensors of Lorentz group. I'll denote them by this letter O labeled by J and N, where J is the Lorentz spin, so the number of traceless symmetric indices, and N is just labeled which distinguishes different operators with the same Lorentz spin. And we also use this index-free notation where we treat the standard traceless symmetric indices for a dependence on some polarization, on some null polarization vector Z. So given that, we can define light transform of O, which is a particular integral transform which depends on the same parameters and x and z. and is defined in some formal way, which is not particularly important, but really what it's doing is it's taking this arguments x and z. It starts the null array from x in direction generated by z, and it integrates our local operator with this null array with some particular weight. And this weight is chosen such that this transform is conformally invariant, which means that if O is a primary operator, then L of O is also a primary operator. And this new primary operator is non-local, but it has some interesting quantum numbers. So its scaling dimension is related to the spin of the original operator, and its spin is related to the scaling dimension of the original operator. It's a bit hard to explain in this short time why this construction is necessary, but just trust me, that's what we have to do. And in this way, we can define Lightray operators as some non-local operators O, J, N of XZ, which have an extra plus minus index. And their point is that they just furnish the analytic continuation of this light transform from integer values of J to general complex values. And so this means is that we can plug some generic complex value of J, you'll get some operator. And if this complex value happens to be a non-negative integer, then this non-local operator will reduce to the light transform of a local value. And the only complication is that it turns out that the analytic continuation has to be done separately for even and odd spins. And so we need to make sure that we choose the correct sign. So O plus furnishes analytic continuation for even spin and O minus for odd spins. And pictorially, you can think about this as by putting all operators in delta J plane. So you can put the local operators to some discrete set of points. And what we expect is that there are some radio trajectories connecting this discrete set of local operators. And if you think about the discrete points as corresponding to light transforms of local operators, then the points on the radio trajectories correspond to this Lightray operators. Now, this is more of a definition of what it means to have Lightray operators, and you can ask, well, why do you think that we have them? And there are several answers. So historically, people have first constructed these operators, although they used slightly different language. They have constructed them in perturbation theory and studied them, certain examples of them in perturbation theory. So more recently, we found that the Lorentzian inversion formula of Kravchuk can be interpreted as corresponding to, in some sense, to this Lightray operators, and in this context, they can be defined as some residues of bilocal integrals of local operators. So we have some formula which can extract this Lightray operators from the OP of the local operators in Lorentzian signature. Now, this definition, it's supposed to be quite general, but this generality is sort of is its curse. So there are some things that I said, some properties of the Lightray operators which you would think are true or would like to be true, and not all of them have completely rigorous proofs from this point of view. And so there are some open problems left to understand how well defined are these Lightray operators in general. But I should also say that we can prove enough statements so that whatever results I'm going to mention can be reformulated in slightly, maybe a bit more awkward language, but which will still be useful and mostly rigorous. So if you are skeptical about Lightray operators, you can at least think of them as a convenient language that you can unpack into rigorous statements. But it's also interesting open problem to understand whether we can just completely trust this picture. Now, so this is what these Lightray operators are, and I would now like to explain how we can use them to compute the energy correlators. And first, let me just as a side remark explain why I'm calling this strange null product of null integrals of energy, source energy tensors, energy correlator. And this was explained by, again, Hoffman-Moldesena, who noted that if you apply a conformal transformation which maps this null plane to future null infinity, then each of these average null energy operators gets mapped to a particular operator, which is the meaning of asymptotic calorimeter, which measures the integrated energy flux exiting through future null infinity in a particular direction. And the small transverse separation of the null lines corresponds to the small angular separation between these two calorimeters. The problem that we're studying is like small angle expansion of energy correlation functions in some kind of conformal collider. Indeed, this observer was also interested in real collider physics and people in theories like QCD. So with this physical motivation, I'd like to understand this short angle or small transverse distance limit. And as I said, Bassina started this question, and they suggested that the leading behavior of the CPU should be given in terms of some particular Lightray operators. However, their statement was more qualitative, where they said that the Lightray operators should contribute, and we would like to understand the precise form of this contribution, and we would also like to describe all the subleading terms. And the way we do this is by trying to first understand the symmetries of the problems of our problem a bit better. And for that, it helps to map this null plane X plus. Instead of going to future null infinity, we map it to the future null cone at some generic point X. And under this map, this product turns into the product of two light transforms of stress tensors. This light transforms are inserted at the same point X. So they have stress tensors being integrated along two different null arrays that start in the same point X. And they have two different polarization vectors which generate these two null arrays. And the limit that we're interested in is when these two null vectors, C1 and Z2, become parallel. This is a nice form because it exhibits the conformal transformation properties very easily. However, because stress tensors have spin, it's a bit technical. So instead, in this talk, I'm going to, just for simplicity of discussion, can replace them by some scalars. It's not going to change anything conceptually, it will just simplify the formula. So everyone is spinning and chasing indices. So this is our problem, is go to understand this OP in the limit of Z1 going to 2. So the first step that we do is we say, okay, let's imagine that there is some OP expansion in terms of some objects. We don't know what these objects are, but let's say there is an OP. Let's try to understand what constraints does the conformal symmetry impose on these things. And unfortunately, I don't have time to get into details of that, but the bottom line is that we find that these operators should be conformal primaries. They will have Lorentz representations, which are, in general, any two-row Young diagrams. So with any length of the second row in particular, which we denote by J, by small j, and called the transverse spin. And the other thing which is constrained about these operators is that their scaling dimension should be equal to 2. Or since we have lots of light transforms, it's also useful to think about this as a light transform of something with spin -1. So this is the question of what can appear. So we have a bunch of vacant spots, and we would like to fill them with some actual contributions. And one way we can get some intuition of what we actually expect to appear on the right-hand side is from the local phi-phi OP. So of course, we don't expect the local phi-phi OP applied on the left to converge, but we do expect that the OP that we're looking for is some generalization of it. The local phi-phi OP only contains trace of symmetric operators that we described, OJN. So it's natural to expect that only their Lightray generalizations should contribute on the right-hand side. At least it's natural, at least for those contributions, we know what the OP coefficients should be because we can just know to continue the OP coefficients of local operators. However, the problem is that these operators are traceless symmetric, so they correspond to one-row Young diagrams. And in other words, in this language, they have 0 transverse spin. So we can only fill in the spot for W, this transverse spin equals to 0. We fill in this spot perfectly in the sense that all the quantum numbers match, and we have the kind of reasonable ansatz, but we don't have any candidates from this point of view for the higher transverse spin contributions. This is already quite good in the sense that it agrees with what Hoffman-Moldasena has suggested and describes the leading terms, but subleading terms require the knowledge of this higher transverse spin. You might imagine that, okay, maybe there's, even though these higher transverse spin contributions are allowed, they are not actually present. This is not what generically happens, and there are relatively simple arguments that you can make for why this cannot happen. And so we really need to find what to put into these vacant spots. And the answer to this problem is quite interesting, and to explain it, let me first consider somewhat unrelated problem, seemingly unrelated problem. So let us focus on the Lightray operator with this index minus and spin j equals 3. So by our discussion, this operator should be related to light transform of a local spin 3 operator. However, one thing that we know about this, so light transform is some integral transform. It takes in a function of x and z and outputs a function of x and z. But what we know about this original Lightray operator, original local operator, is that it's a polynomial function of the polarization vector because it was just the traceless symmetric tensor. After applying this light transform, this property is obscured, and you can ask whether we can still detect that the light transform is applied to something that's polynomial. And you can check that indeed this can be done. There exists a differential operator which involves derivatives with respect to both position and polarization, which acting on this light transform gives 0. And the way you see this is you write out this light transform as an integral, you do some integration by parts, then you find that under this integration by parts, the x derivatives vanish, disappear, and you only have a bunch of z derivatives which act on the local operator. And since the local operator is polynomial, when you have too many derivatives acting on it, you get 0. So we have the shortening condition for this light transform, but this is the same as light transform is the same as our Lightray operator. So we see that there is some shortening condition which is satisfied by this particular Lightray operator. Conformal field theory shortening conditions have to be conformally invariant because otherwise you can apply conformal transformations and prove that the operator itself vanishes. But conformally invariant shortening condition is known also as null state, or in other words, a primary descendant. And usually we don't pay too much attention in higher dimensions to such situations because they only appear in conserved currents, and these null states or these shortening conditions should always be satisfied. Null states should vanish. This holds from the entirety for local operators. So for these non-local operators, this actually doesn't follow automatically. And here we were only able to find that this shortening condition is satisfied because we managed to relate this Lightray operator to the local guy here. So more generally, we could, even though this primary descent exists, it could happen that it wasn't 0. We don't have an independent argument for it being 0. But this allows us to play a seemingly stupid game because we have this index minus here, and we can just go ahead and replace it by plus. These two operators, O plus and O minus, have completely the same quantum numbers from the point of view of the shortening condition. However, this operator O plus has the wrong sign for the parity of the spin, so it's plus, but the spin is odd. So it's not obviously related to any local operator. And what it means is that we now have this primary descendant of this O plus j equals 3, and it might be equal to 0, similarly to the O minus, or might not be equal to 0. And you can check in some examples, and you see that it's actually non-zero and it's not vanishing. But if it's not vanishing, it's some new primary operator that we didn't know about before. So it's interesting to ask what are its quantum numbers. And if you work them out, you find that they precisely such that they transform like you expect this contributions to do PE, this transfers spin 4 to transform. So secretly, this differential operator has some extra indices which produce this required transfer spin. And of course, there was nothing special about the spin being 3, so we can generalize this to any given integer spin, and we find that we can now have a conjecture what can fill in the spots for all this contributions to the P, and we can then make this ansatz where we have now sum over all possible transfer spins, and there the contributions to give these transfer spins are this primary descendants in various Lightray operators. If the transfer spin equals 0, we just get the Lightray operator itself. So we have this ansatz, and the only thing that remains is to understand this coefficient function and various normalizations and so on. So as usual in conformal theory in P, it turns out that the coefficient function is fixed completely up to coefficient by conformal symmetry. So we only need to understand what the P coefficient is, but the P coefficient can be conjectured to be just a deconcatenation of the P coefficients of local operators. And then we have some conjecture for the formula, we need to fix some normalizations, and we need to decide whether this conjecture is correct or not. So we need to prove this formula. So it turns out that you can both fix the normalizations and prove this formula by a relatively simple argument where you apply some simple formulas from harmonic analysis on Lorentzian, on Lorentz group to the left-hand side, which basically inverts this OP and tells you what this W's actually should be in terms of some integral of the left-hand side. And by comparing these formulas to our definition of Lightray Creators, you can conclude that this is indeed the correct form and also work out all the required normalizations, and you find very simple and natural formulas. And of course, after we have derived this formula, we can also try to verify it, and we have indeed successfully verified it to hold an n equals 4 super-Nielsen from coupling in many stations, and it works beautifully every time. So I'll stop here with a quick summary and just a couple of open questions. So hopefully I have explained that we have this interesting structure as Lightray Creators, which are very useful for describing interesting physical observables. And there is also a non-trivial structure of their Verma modules, which appears for some special discrete values of J and plays its own role in describing these observables. And there are some open questions, and I think the most open question that's begging to be answered is the question of whether we can write some kind of more general P of two local operators, which will contain both local and non-local contributions, but will have the feature that, unlike the local P, it will be convergent in more scenarios, so that we would be able to derive things like conformal Regge theory or this Lightray, or this energy OP by just the special case of this formula. And more generally, it's also would be nice to understand kind of how rigorous this whole picture can be. As I said, it's mostly rigorous now, up to some things that we don't understand, and it would be interesting to understand whether progress can be made on this question. So it would be also help with understanding things like whether the Regge trajectories are isolated as we sometimes expect, or do there exist some Regge cuts. And if we understand the structure of these Regge trajectories, we can also start asking interesting questions. For example, can we use the structure of Regge trajectories to learn something new about the spectrum of local operators as a whole? So I'll stop here, and thank you very much for your attention. Thanks.
Thank you. So I brought this to check if there are questions online, but I give priority to questions from the audience. So I had a question, Petr. So you mentioned that you tested all of this in n equals 4, but can you be a bit more explicit, like when you actually compute these energy correlators in n equals 4, and then you use this OP, what kind of singularity you predict when two detectors come close together as a function of the angle? What is the structure of this OPE?
Sure, thanks. So first of all, what we do is use other people's results. So people have computed these energy correlators. So first of all, the energy correlator in n equals 4 can be related to some scalar correlation function using supersymmetry. And then it's been computed to many loops by various groups in weak coupling expansion, for example. And then you can try to reproduce this result in small angle limit by using known OP data and some definition and spin. And what this formula predicts is, of course, something relatively natural, is that you have to, for example, for the leading singularity, you have the angle to the power, which is the anomalous dimension of spin 3 given spin trajectory Lightray operator, which is like, so you take the trajectory in which the stress tensor lives, and you know to continue to spin 3, where there is no local operator because it's even spin, and you take that normal's dimension, and there is, of course, it's known from integrability very well, and so on. You can predict the singularity to be some power law. And sometimes it's singular, and sometimes it's non-singular, and this depends on the value of the coupling.
So, but do I understand correctly? Is always power like the normal, like the OPE of
Yes.
local operators?
Yes. So in fact, I didn't mention this, but this OPE, so kinematically, it's the same as d minus 2-dimensional OPE. So this coefficient functions are just d minus 2-dimensional OPE kernels. So they have the same power laws and so on.
Okay, thank you. Any other questions?
I have a question, if I can, from the sky.
Yes, go ahead, Clay.
Yeah, hi. Can you go to the last page, Peter? The conclusions? I wanted to ask some about this, some future directions. So obviously in two-dimensional CFT, realizing that there could be null states led to enormous in CFT. You know, there's this Katz determinant, and there are special models where there are extra null states and things like that. Is there any chance that there is something like that in higher dimensional conformal field theory, but where the null states are not in the local operator representations, in those related to light rays or other extended operators?
I had a bit of trouble hearing your question because of connections, but I think you're asking about whether anything similar to what we do with null states in 2 dimensions can be done in higher dimensions, perhaps with Lightray operators.
Yeah, what I'm asking is whether there can be extra null states in the spectrum of light ray operators that are model dependent, and maybe those models that have extra null states are special.
So it's an interesting question, although I'm not. I think so. Let me just make one statement which will clarify this hopefully. So to have null states, you need some norm in your Riemann module to vanish, and this is one equation. So you pick some descendant and you want its norm to vanish. The vanishing of this norm is one equation that you need to solve. And with this Lightray operators, you have one complex parameter j, so you can always solve this equation essentially. So in this, on this Regge trajectory, you expect that there should be some discrete set of points, and this discrete set of points, in any theory, there should be null states. And so in principle, I think this suggests that maybe it's not as optimistic in the sense that there are always some null states. They can play some role, but maybe it's not so theory specific. But you could also imagine that some interesting stuff happens at these discrete points. Maybe there are some intersections of Regge trajectories, and maybe some interactions with local operators.
But do the discrete points give rise to differential operators that act on correlation functions and therefore give you constraints?
Yes, they give rise to differential operators, but you have to ask whether these differential operators actually annihilate anything. So just because the Riemann module has a null state, it doesn't mean that this null state is 0 as an operator. So here, for this construction, it's important that these null states are actually not 0 as operators. So if you now insert this, guy into some correlation function and apply this operator, you don't get 0. But sometimes you do.
For the minus one we did, right?
For the minus guys, yes, we did. So
that's some differential equation on the correlator of that O minus operator?
Yes, but this one is relatively boring. It's, for example, if you consider its 3-point functions, well, that differential equation essentially tells you that this operator is coming from a local operator. So probably an interesting question is whether there are any certain conditions which are not obviously satisfied because they're related to local operators, but which still are actually satisfied and actually give some interesting information.
Mm-hmm. Okay, I actually had one more question on the end slide, if I'm allowed to go.
Go ahead.
It's up to the moderator.
Yeah, go ahead.
Yeah, so this, can we find an overarching OPE of the rough form let me just cast a little shade on that and see what you think, which is, why should it only, if you're going to extend to non-local operators, why should you only involve line-like operators? Right, like in gauge theory, in quantum field theory, we know that there are surface operators or other kinds of operators that cannot be expressed as smeared local or lines. So that's a kind of another dimension that we could go into. And why wouldn't we expect that we need to involve all of them?
Very good, thanks. So first, let me So let me say, first of all, that Lightray Creators is a bit of an unfortunate name because I think that's what we've been called historically, but in practice we know that there are examples of them which are not supported on a line, but instead on an altcone. But you can, of course, then start asking, well, why it has to be an altcone? Why can't it be like a full dimension zero thing? And I don't know. And
but is there some reason to expect why the dimension would truncate in this formula, in this OPE formula? Or maybe I'm not understand the first response. Are you saying that the mathcal O summation there includes what I would call surface operators also on null surfaces?
So these guys are just supposed to be local contributions, which have to be there because we know that this product does not fill the vacuum. But the Lightray Creators, so what I'm saying is that they're called Lightrays, and this is a historical name, but we have explicit examples of these operators, which is still called Lightray Creators, which are supported on altcones, so it's something that you would call a surface operator.
I see.
Completely. So you could still maybe complain about that, but the best answer I can give to your general shadowing of the suggestion is that it would be great if we had an example where we can be able to compute something and the Lightray operators wouldn't be enough. So where we would see some new kind of objects appearing.
Okay. Thank you.
Okay, if there are no further questions, let's thank Petr again for the nice talk. And Clay is clearly ready to continue.
Okay.
So we will continue. So the second and last talk of the session will be by Clay Cordova from the University of Chicago, and he will tell us about Calabi-Yau conformal field theories and random matrices.
Okay, you see my screen?
Yes.
Okay, great. All right, well, thank you very much for the invitation. I regret that even now I'm still not able to be there in person. Okay, so this is the title of my talk, Calabi-Yau CFTs and Random Matrices. And it's based on a paper that appeared recently, this paper here, with these two collaborators, Anthony Ashmore and Nima Afkami-Jetty, both of whom are postdocs here with me at UChicago. Keep an eye out for them. Okay, let me summarize the main results. So this is a computational paper. So our main result is that we're going to compute the spectrum of operator scaling dimensions. And just to latch on to Peter's talk, we're talking about local operator scaling dimensions here in certain 2D conformal field theories. And these conformal field theories will be of a very famous kind. They are sigma models into Ricci flat Calabi-Yau target spaces, so Calabi-Yau manifolds. And of course, as much as we would like to know the metric and spectrum and everything about those Calabi-Yau CFTs, despite many decades of study, people don't know the analytic metric for Calabi-Yau. So we will proceed numerically. So we're going to compute the metric and the spectrum numerically. And after doing that, we're going to average over some marginal operators in these CFTs, some marginal couplings. to make an ensemble of conformal field theories. And we're going to show that the spectrum in this ensemble has the same statistics as the Gaussian orthogonal ensemble of random matrix theory. So that will be the main goal of this talk. It is just to flesh out this series of calculations and plots. Before getting into that, let me give you some plots. So you see what I mean by show that it has the same statistics. And don't worry if you don't understand all the terminology here. I will explain it as we go along. But OK, so here are some plots for the quintic Calabi-Yau threefold, the famous quintic Calabi-Yau. Here's an example. This is the so-called spectral form factor, showing some statistics of the energy levels. It's the Fourier transform of the two-point function, as we'll discuss later. So the blue curve is what the Gaussian orthogonal ensemble of random matrix theory predicts for this quantity. And the orange curve is the result of the calculation using data extracted from the quintic. And OK, there's some ring down behavior, which we'll talk about later. But what I would like you to focus on is that after a while, there's a nice match between these two quantities. Similarly, we could look at nearest neighbor statistics. And here I've not only illustrated the Gaussian orthogonal ensemble, but also the unitary ensemble in blue and the symplectic ensemble in this yellowish orange color. And that's to be compared to the data from the quintic. And again, you see a good fit. So we'll talk about this. And finally, there's long-range spectral rigidity. So again, here we see the various matrix ensembles and also for comparison, Poisson statistics, and then the data from the quintic, which are these black dots here. OK, so these kind of plots are the results of this project. And the comparison to the matrix model is the highlight. So I'll tell you more about this now. OK, first, what is our motivation for doing this? So one motivation is that random matrix statistics is a hallmark of quantum chaos. And I put definition here in parentheses. You might think that the statistics of random matrix theory are really the definition of chaos in a quantum system. There are various other diagnostics, but this is one possible definition. And there are these very famous conjectures, the Bohigas, Giannoni, Schmidt conjectures, which highlight this, and they state that quantum systems whose classical limits are sufficiently ergodic show random matrix statistics in their energy levels. Now, sufficiently ergodic is kind of vague, and indeed it is not known what exact precise kind of ergodicity in the classical limit is needed to guarantee this random matrix statistics. In practice, people in physics just study this in examples, though I think there is some progress in various classes of systems proving this. Now, of course, in high energy physics, recently there's been a lot of excitement about studying these kind of chaos questions in the context of black hole physics. And there, the black hole energy levels are discrete, non-degenerate, and chaotic, and hence show the statistical properties of random matrix theory. So here I've highlighted just a couple crucial references for that. OK, so let's now start moving towards the main question here. So the appearance of random matrix theory in black hole physics suggests via holography that generic conformal field theories might also display chaos. What would I mean by that? So we're going to look at the spectrum of a conformal field theory quantized on the sphere. And this spectrum is discrete. And it has eigenstates that are dual to the local operators. So the Hamiltonian D acts on a state O and gives some eigenvalue DO. So D is the scaling dimension of this state dual to the operator. And so what we'd like to know is, given some ensemble of conformal field theories, what are the statistics of these scaling dimensions, these eigenvalues di? So of course, you might think, based on holography, that these should have something to do with random matrix statistics, but there are main challenges here. There are several challenges to overcome. The first is that you need generic conformal field theories, right? This is certainly not going to be true for a free or rational field theory. And the second thing is that you need an ensemble of theories. So not only do you need to be able to find this spectrum for one theory, but you need to somehow vary the parameters to generate an ensemble. So those are the two things we want to do. So we're going to carry this out in CFTs defined by sigma models into Calabi-Yau target spaces. So these have 2, 2 supersymmetry, and they are irrational, so they are not exactly solvable. Their central charge is given by this formula, 3 times the complex dimension of the target space that you happen to be looking at. So for instance, for the quintic, that's a C equals 9 theory. For K3, that's C equals 6. These are extremely well studied field theories, particularly in the context of applications to string phenomenology and mirror symmetry. But I'd like to point out that, especially in the latter application to mirror symmetry, the main focus is on observables protected by supersymmetry. And that is not our interest here. Our focus here is on the generic operator spectrum in this model. So these CFTs naturally come in families, and that will be useful for us for making an ensemble. Specifically, they have moduli that are factorized into a product of 2 pieces. The first are the Kähler moduli. These are exactly marginal deformations of the CFT that correspond to changing the size of the Calabi-Yau. And then there are also the complex structure moduli. And these are exactly marginal deformations that change the shape. And so we're going to make a family, an ensemble of CFTs by fixing the Kähler moduli and wiggling the complex structure moduli. Okay. How can we make progress? To make progress, we're going to study these CFTs in a limit where the Calabi-Yau target space is large. In this limit, the spectrum of Virasoro primaries looks like operators of the following form. So there'll be an operator, a local operator O, which looks like some object omega. Omega depends on the target space position. And then there are also, it's decorated with a product of fermions, lambda and psi. The details of this are not too important, but for those of you who are familiar with 2, 2 sigma models, I flash it for you here. So the lambda and psi are 2 kinds of fermions. And these operators are eigenstates of the Hamiltonian, eigenstates of scaling dimension, if this omega is an eigenform of the Laplacian acting on the space of p comma q forms in Dolbeault cohomology, in Dolbeault notation. So what are the quantum numbers? So the scaling dimension d is given by p plus q over 2 plus the eigenvalue of the Laplacian. That's this lambda. And the spin is p minus q over 2. So these are the operators that we are studying in the large volume limit. So, of course, in that large volume limit, the eigenvalues of the Laplacian scale down towards 0. And this means that the most important light operators that we'll be studying are those associated to scalar eigenfunctions. So I'm going to focus now on the scalar eigenfunctions, though adding the forms is easy. And physically, you can think that this is the limit where the spectrum of Virasoro primaries is the same as the energy levels of a bosonic particle moving in the target space Calabi-Yau. So if I connect back to this famous BGS conjecture about chaos, we would expect chaos in this spectrum of primaries, that is random matrix theory statistics, if the classical geodesic motion on the Calabi-Yau target space is ergodic. Now, that's not clear whether it should be so. The Calabi-Yau, okay, it's a complicated manifold, but the metric is very special. Okay, so let's try to state what computational goal is now. So our goal is to compute the spectrum of the scalar Laplacian on a Ricci flat Calabi-Yau manifold. So we're going to work numerically, and we will extract the first couple hundred eigenvalues. We're going to carry out this procedure for many different points, some large number, like 1,000 points in the complex structure moduli space. And by collecting all this spectral data, we'll make a big pot of eigenvalues. This will be our spectral ensemble. And when we're done, we're going to compare the statistics of this ensemble to random matrix theory. Okay, so now let's get into a little bit of detail about how one does this in practice numerically. So we will compute the Ricci flat metric and spectrum using an algorithm introduced by Donaldson. And this is really the key technical thing that we need. I mean, it would be nice if we knew the analytic form of the metric on a quintic and could do calculations with it, but we don't know any analytic Calabi-Yau metrics. So we have to proceed numerically. So what do? You begin with a Calabi-Yau, for instance, your favorite threefold, and it's defined by a hypersurface equation in projective space. So the quintic is defined by a degree 5 equation in complex projective space of dimension 4. And the first thing you do is you pick an n, and you consider polynomials. I'll call them S alpha. Alpha just labels the polynomials of degree n. These are polynomials on the hypersurface. And from these, you can construct a Kähler potential as a linear combination. So the Kähler potential K is written as log S alpha, H alpha beta bar, S bar beta bar. So these S bars are the complex conjugates of the S's. So the S's were holomorphic polynomials of some fixed degree. And this H alpha beta bar is just the coefficients. So they're just some numbers. So this K depends on this integer n, the scalar potential depends on n, and on these choice of numbers h. And you could think that this is going to give a generalization of the Fubini study metric. And then we're going to reduce it onto our hypersurface. Okay, so this so far is not a Ricci flat metric. It's just a way of parameterizing a class of metrics. Now, we're going to iteratively optimize these coefficients, h, to minimize the Ricci curvature of the metric. And what Donaldson did is to introduce an iterative procedure that will eventually reach a minimum given a fixed n. Okay, so I won't explain to you what that operator is, that iterative procedure for reaching the minimum, but I will just say that after iterating that procedure and taking n to be large, this procedure eventually would converge to the Ricci flat Calabi-Yau metric. And numerically, it's quite good. So numerically, so here's an example for reliable numerics, for reliable numerics on the metric. Say knowing the components of the metric at several decimal precision, this algorithm takes you about 5 minutes on a typical laptop for a given quintic. And practically, this is good enough for us. So our goal is to run the optimization at large enough n to achieve this desired spectral precision. So 5 minutes was good enough for us for a fixed Calabi-Yau. So what's the next step? The next step is, given the metric, you need to numerically compute the eigenvalues of the Laplacian. So how do you do that? Well, if you numerically have the metric, that's not such a big deal. So you pick a finite set of functions, and you want to think of this set of functions as some kind of approximation to the infinite dimensional of all functions on the Calabi-Yau. So for instance, working with those polynomials S alpha, we could take the functions to be S alpha times S bar beta bar. So like products of S's and their complex conjugates, suitably normalized. And acting on that set of functions, the Laplacian could be approximated by a finite dimensional Hermitian matrix. And what we need to do is diagonalize this matrix numerically to get an approximate spectrum. And of course, increasing the size of the basis, that is, say, the degree of these functions S, improves the number of eigenvalues that you can access reliably. So again, just to give you ballpark for how computationally expensive this is, after you've got the metric, if you want to get a few digit numerical precision on 100 eigenvalues, this requires another 5 minutes on a typical laptop. Okay, so after all this numerics, which I just sketchily explained, we end up with order 100 eigenvalues reliably computed. And these, of course, translate into scaling dimensions of operators in the conformal field theory using the sigma model dictionary that I explained previously. Now, this is not yet the final step. Of course, we also want the ensemble of conformal field theories. Now, implicitly, each spectrum that we have just computed depends on the complex structure moduli. Let me make that precise. So the complex structure moduli are encoded in the hypersurface equation that you use to define your Calabi-Yau. So here I've written the equation for the quintic. It's a hypersurface equation. 0 equals some sum over coefficients C with some indices times products of 5 z's. So the z's you could think of as homogeneous coordinates on the projective space, and the c's are numbers. And the coefficients C, these are the complex moduli. And by varying them, you change the shape of the Calabi-Yau. So what we'll do to make an ensemble is we'll say sample, we'll compute the spectrum for a sample of different C's. Practically speaking, what we did is about 1,000 C's uniformly distributed over a ball of a fixed radius around the origin. Okay, so now we have our ensemble. We have computed scaling dimensions for an ensemble of different 2D conformal field theories. And our task now is to compare this ensemble to the statistics of random matrix theory. So the most famous result in random matrix theory, I'm sure by far, is that the density of states at large n, I will always be at mostly be at large n in the size of the matrix. N is the size of the matrix. So the most famous result is that this density of states is given by a semicircle. So here's rho of E, and there's this famous Wigner semicircle. And it's a bit ironic that despite the fact that this result is so famous, it's actually not this result that is universal or applicable to general chaotic systems. So general chaotic systems do not exhibit a semicircle in their density of states. And instead, what you're really interested in is the statistics of higher point correlation functions after normalizing out the density. And so that's what we'll be focused on here as well. So the first universal feature to look at is the so-called level repulsion. So the probability of finding a distance S between sequential energy levels sequential eigenvalues in the matrix takes this form. So there's a Gaussian exponential suppression, but there's also this multiplication by S, which causes the maximum to be away from the origin. That's the level repulsion. And of course, you're supposed to contrast this with Poisson statistics, which just has this simple exponential fall, this e to the minus s. And this function, P of s, this nearest neighbor statistics, depends on all the higher point correlation functions in the matrix model. So that's one thing that we're looking for. Another thing to examine is the 2-point function. So this is the absolute probability for two eigenvalues, not necessarily nearest neighbors, to be separated by s. And at large n, this is given by this simple formula, relatively simple formula. So what should you, the details are not too important, but what you should see here is that, first of all, ignoring this everything but the 1. So this 1 is a disconnected piece. And then there's also a connected bit, that's g minus 1. And it's decaying as a power law, like s to the minus 2. And from this, you can see various interesting features. For instance, the spectral rigidity. So typical fluctuation in the number of energy levels over a large interval of size L scales as square root of log L. That's this number sigma of L, sometimes called the number variance. And that's very different than a Poisson process where it would be like square root of L itself. So there's a log here. And finally, let me point out one other thing that people often talk about is the spectral form factor. And this is the 2-point function, or at least the connected part, viewed in Fourier space, in complex Fourier space. So we've taken g minus 1, and we do a complex Fourier integral here, and we get a function of t and beta, which are like real and imaginary Fourier parameters. So what does this look like? So here I've drawn a plot for you. The blue is the spectral form factor at infinite n. It has this feature of a growth up from ramp, and then it becomes constant. That's called the plateau. And at finite n, say n equals 100, there's kind of non-universal ring down behavior where you have this sequence of oscillations, this infinite sequence of oscillations, but they get more and more damped until they match onto this blue curve. Okay, so these are the various statistics to look out for. And so now, with this information, we can compare our results from the sigma model calculations to the expectations from random matrix theory. And explicitly, the Calabi-Yaus that we considered are the K3 surface and the quintic Calabi-Yau threefold. Though with more time and energy, one could really do this for almost any Calabi-Yau. So here, for example, is the eigenvalue density, the 1-point function for K3. Okay, it's very wiggly, it's got some interesting features, and your first thought might be, well, this doesn't look anything like a semicircle, so your project is silly. But as I explained to you before, that's okay, because you're not looking for random matrix statistics in the 1-point function. That's not universal. Instead, you want to look at how do nearby energy levels correlate with each other, or far away energy levels correlate with each other, normalizing out the density. And here we've done that. So here is, for instance, the nearest neighbor statistics for K3. This is function P that I was talking about. Again, I've shown the 3 different famous matrix ensembles, and the gray is the actual data from the K3. Here's the long-range spectral rigidity. You see this square root of log behavior here, or this is sigma squared, so it will just be log behavior. And here is the spectral form factor. Just like a finite n matrix model, the K3 has some kind of non-universal ring down behavior, some series of oscillations here. But then, after a while, it matches on to this ramp and plateau behavior. So it shows the characteristic behavior that we expect for the n equals infinity GOE. Now, of course, I already showed you the quintic. It has a similarly nice agreement. Again, spectral form factor, nearest neighbor statistics, and number variance all show good agreement to within our numerical precision of expectations from random matrix theory. Okay, so let me come to the conclusions. What have we shown? We've shown that the light spectrum of sigma model CFTs, at least these interesting Calabi-Yau ones, in the large volume limit, is well approximated by random matrix theory. And there are many open questions, but I will highlight a few that I think are interesting. One is the interplay with modularity in 2D CFT, or more generally, considerations of conformal bootstrap type. So we have seen that random matrix theory predicts some features of the energy spectrum, the spectrum of scaling dimensions, and it would be nice to understand how those predictions interplay with other constraints on conformal field theory. Another thing that we're currently working on are other spectral statistics. So I highlighted some of the famous ones, the nearest neighbor, the spectral rigidity, the spectral form factor, but random matrix theory predicts a lot more. And so you could ask, which of those are applicable to these generic CFTs, this ensemble of CFTs? So one that we're currently thinking about, for instance, is the gap. What is the statistics of the lightest non-identity operator in the conformal field theory, or the lightest eigenvalue in the Calabi-Yau? And finally, one kind of interesting thing I'd like to point out is that we're essentially here at weak coupling. We're in the large volume limit. So we're at weak coupling, but we computed a huge number of states, hundreds of states. And you could ask whether this is really universal, that we should have seen random matrix statistics in this limit, or whether we just got lucky. And that I don't have a clear answer for you yet. Okay, so thank you for your attention. I'll stop here and take some questions.
Thank you. Questions?
So there's this idea that the K3 moduli space, the rational points are dense. Would that have any impact on your calculation, or would you see any imprint of that?
I think that we're too coarse or kind of not smart enough yet to see something of that specific of a feature. I mean, there have been some papers trying to study orbifold points and statistics at orbifold points and things like that. There's this paper by Oguri and others. But yeah, we haven't. Let me get back to you, basically, hopefully with more information.
Yeah, so do you have an explanation where do you get GOE? Can you get with other
you mean by the O?
GOE or GSE?
Yeah, I think that's just because the theory that we're interested in has some kind of like time reversal symmetry. Has some discrete Z2 symmetries that are putting the O. You can break those symmetries with other sigma models. It's just that the 2,2 sigma model has the symmetry, is of the symmetry type that you would expect for the O.
You showed various plots, and one of them was the rigidity.
Yeah.
And one can see that the so the numerical values with growing L go above the GOE prediction. I guess that is just a reflection of what we see in the left upper corner. You have this deviation from universality at short time, and that presumably translates into a deviation from universality in the energy picture for large energies. Is that correct?
That is correct as far as we understand. It's a little bit difficult right now for us to disentangle which part of this deviation here is numerics and which part is due to the actual deviation from universality here. So we're running these kind of calculations again with better precision to see what happens. But yes.
And the other thing I'm not clear about is taking the large volume limit.
Yeah.
So I'm not into Calabi-Yaus and things. So you fix, say, a K3 surface, and then you still have a way of scaling up the volume, or do you have to vary the Calabi-Yau to get to big volume?
No, you fix the complex moduli of, say, the K3 surface. So we fix, say, the hypersurface equation. That's fixed. And then you scale up the overall volume of the metric. So just take the metric, the Ricci flat metric, and multiply it by a big constant. And that has the feature that it makes the spectrum of the CFT map onto the spectrum of the Laplacian. So that's why we did that, because then that becomes a kind of accessible calculation. So that's for a fixed complex structure, and then we make our ensemble by varying the hypersurface equation.
And you only talked about the scalar sector, but at the beginning you mentioned that your 2,2 theory, of course, also has one forms, two forms, the other stuff that is in supersymmetric quantum mechanics. Have you looked at that, and do you see similar features there?
We have looked a little bit at it. So it's a little bit more numerically expensive to look at the spectrum of forms. So we kind of need a little more time, but early results seem to also show random matrix statistics there as well.
There is one question from the forum, so from Mark Mazet. So he asks, what corrections does the formula for operator dimensions receive for finite but large volume? If we go to the heavy operator limit, does your formula still apply, or the heavy operator and the large volume limits don't commute?
Yeah, so generally speaking, you should think that the primaries in the large but finite volume limit are split into this sector that is related to forms, and then what's called the winding sector, which will be related to closed geodesics bucket space. And so for each closed geodesic, you will get an operator. Those are like the solitons, the solitonic operators. So they have scaling dimensions that are going to infinity in the large volume limit. But in order, so there will be corrections at finite volume once you get to large enough scaling dimensions on these operators where they could start to mix with the winding sector. Now, to answer your second question about the limits, they do not commute. And one avatar of that is that the Cardi growth is not seen in just this set of operators. To get Cardi growth, you need to include the winding sectors as well. So it's not as if, so although we compute, say, a lot of operators in human terms, like a couple hundred operators or whatever, it's not as if we are accessing the generic heavy operator spectrum of the CFT. And that is in part why I brought up this question here at the end, which is that maybe it's a little bit surprising then that just by studying these sort of leading lightish operators in the large volume limit, we're still getting these generic RMT type statistics, or this what you might expect is generic statistics. So that's an interesting feature that I think deserves better explanation.
Okay, Clay, I also had a question about the averaging. So you emphasized that you needed this ensemble, but I thought that even for a fixed Hamiltonian, if you just go high in the spectrum, you have many, many energy levels, so you can still study for a fixed Hamiltonian what is the distribution of the, say, the consecutive levels and things like that. So for example, concretely, if you just take one fixed Calabi-Yau and you plot your spectral form factor, do you get a completely different curve or before averaging?
It will look extremely erratic. I mean, it would just be like a sequence of points that just wildly oscillate up and down in the picture here.
So even at late times, it won't. It will oscillate around that ramp.
It will oscillate. It will jump around the blue. Yeah.
I see.
Yeah. So you know, there's this very kind of what looks like noise here at the tail end of this curve is coming from that the ensemble average is averaging out kind of big individual fluctuations.
I see. Thank you. Any other question?
Also ask a question? Can
you
hear me?
Yes, I hear you.
So you said that in order to average or the complex modular, you just pick the ball in the space of this equations and just averaged with like uniform measure. Is this important? Like, if you is this like the right way to do this? If you change it, does it change the results?
No, it does not change the results. But if that's in part because our average was sort of over a small ball, so that's why I'm confident in saying that. So in principle, you might have said, well, there is a natural metric on these moduli coming from the Zamolodchikov metric, which comes from the two-point function of the associated exactly marginal operators. And if you were smarter than me and were trying to do an exact, say, average over the entire moduli space, including points very far away, then I think you would have to be careful about the difference between uniformly averaging and averaging with the Zamolodchikov measure. Now, for our purposes, we are averaging over a small ball where the measure isn't varying very much at all. So I think this is a very tiny correction numerically in our plots.
But this region is still big enough for you to see all this kind of smoothing out and spectral function.
Yeah, indeed. That's not that surprising. I mean, I think that's in some sense related to Joao's question, which is that people often talk about random matrix statistics for a single quantum field theory. And often what they mean there is just you do take the individual quantum field theory and do some very minor averaging just on its own spectrum. Like maybe just a little bit of time averaging. So coming back to this question about the spectral form factor, if I literally just plot the spectral form factor for a fixed CFT, it will look very erratic. But if I do some very small self-smoothing, like averaging in time just on an individual CFT, it will again become this plot. So you can think that maybe the ball is just playing a role of doing some small self-averaging. Because the eigenvalue is not varying that much.
All right, I see. Thank you.
Okay, I think Mark was asking exactly the same thing about time averaging, but you just answered, so it's okay.
Okay.
Any other question? Okay, if not, let's thank Clay again for this very nice talk.